Thank you, Raik, and welcome everybody to our session. You probably know the session title, but essentially the session is about cyber security situation awareness. And basically it means that how we really know where we are and what we need to do. So it essentially involves sensing, perception, comprehension, and future situation prediction. I just want to let you know that after the situation awareness is a second important stage, which is cybersecurity situation decision-making and control. We are not touching it, but I hope maybe next year we talk about situation control also. So, we are living in a very happy time. There is a very important, paradigm shift in cybersecurity where we are slowly moving from IT-centric cybersecurity to mission-centric cybersecurity. At the same time, we see paradigm shifts in the enabling technology. So, few words that make sense to remember in the future technologies in terms of AI is a cognitive and collective, which both leads to so-called emergent behavior, in our sense, resilient systems. So I would like, we try to focus on that, the situation awareness part, but definitely when we deal with situation awareness, we have to take account future situation control issues. So we're happy to have our great session speakers. First from left from me is Roman Graf. He's from Austrian Institute of Technology in the cybersecurity department with Dedicated Center. And he has many interest in cyber risks and many European projects that he has involved. Second, in the middle of Steve Earle from a company you probably know from Midra. And he has worked also in the cybersecurity area many years on impact analysis and using AI technologies for that. And last not least is my old friend and colleague from Tallinn, Professor Leo Mutus from Tallinn University of Technology. Many years he has led laboratory on proactive technologies, and now he's taking part one of the new, hopefully significant projects in Estonia on cyber situation awareness. So, Roman, are you ready?
Yeah. Can I start?
Yeah, please. What we do, we have 15 minutes for each speaker, and after that we have a joint QA session.
Thank you for introduction. I was working on this tool together with my boss, Dr. Ross King, and I will talk about a tool that should support cyber analysts in Security Operations Center for cyber incident analysis. And how can I get next slide? Okay. I will briefly give a brief introduction and challenges that we have in situational awareness analysis, and then I will touch two big topics. First is neural networks, and second is blockchain. Of course, I will just briefly inform about this, just to understand why we use these technologies. Then I will briefly explain which alternatives we have for this solution, which tools are possible to use instead of these two topics. And I will proceed with our proposed solution and turn to system design and incident processing. In this topic, I have two big blocks. One is incident classification, where we're using autoencoder neural network. And second is the incident management using smart contracts based on blockchain. And I will conclude with experimental evaluation. It's very complicated currently to protect CI critical infrastructure. If I say CI, I mean hardware, software, or documentation, and it's increasingly targeted by sophisticated cyber attacks, and is protected by increasingly complex tools. And these tools produce a lot of outputs that are very difficult to analyze for human. And there is a need to automatize handling of at least part of this information because it's not possible for human. And one of the challenges here is to find relevant information in these large data sets and to get additional intelligence from this. And second challenge is speed of events. It must be in real time. And data overload and meaning underload. So we need some sophisticated tool for that. So our goal is to replace human by this triage process when he looks for similar incidents. So we could automate some of the tasks here. And our group was working on Caesar tool in ECOSIAN European project. It's one of threat intelligence platforms that are on the market now, but it's proprietary, and you have link here. You can look more information there about this tool. The goal of this threat intelligence platforms is parsing and correlating of information, discover unknown content, and collect indicators of compromises and vulnerabilities if they are found. Another commercial tool is Electric IQ, one of the samples that are widely used. And free tools are MISP and Intel MQ. Intel MQ is used by Austrian CERT and some other CERTs, but it's quite simple tool, so just there are no some sophisticated methods. And MISP tool is widely used also in military and in civil for information sharing. There are special standards and ontology. What is neural network? Neural network is imitation of human brain, and it makes parallel computation. We just model neurons, and in our neural networks we have for each neuron weights and activation functions that can be linear or not non-linear. And during the training of neural network, we just adjust these weights in back propagation when we know which error occurred. And we made different iterations for our training. And then if system is trained, then it can either classify for supervised learning or cluster or reduce dimensionality for unsupervised learning. These are two main types of neural networks. And in the first case, we have labeled data and won't classify. And in second place, we don't have trained data, and just system learns how to present structure of data. And we use this dimensionality reduction in autoencoder neural network. In general, when we build neural network, we just collect a lot of examples, specify correct output for given input, and create program so it is effective, fast, and scalable for similarity search in case of autoencoder. I will explain a little bit more about this technique. Blockchain features are first feature that non-trusting members can interact with each other without central authority. And there is a consensus method, different kinds of them, proof of work or proof of authority. They apply to find consensus that say nodes decide is this transaction correct or not. And there is also mining idea in blockchain, but we can use this test tool without mining because it doesn't make sense for us. It's not cryptocurrency. And we just can use proof of authority. And blockchain doesn't need human interaction. And we expect that this method can reduce human involvement and support us by life cycle management. and also manual analysis costs, because then cyber analysts can focus attention on really urgent incidents. And there is a smart contract that we use. It's just a program code in specific language, Serpent, that is quite outdated now, but is Solidity, another language. And we program rules in this program in smart contracts, and it will be triggered, and this rule cannot be changed. It's a big advantage, and state of this smart contract is stored on all nodes in blockchain, so it cannot be removed from there. And the idea why we apply blockchain is that we want automatically make obvious and predefined decisions. So if institution has defined the threats and they made the risk analysis, then they know which processes they can automate. In each institution, it will be different. So autoencoder reduces dimensionality. So usually there are different alternatives like support vector machine, embedding neural network, GenSim, decision trees, naive bias that can be applied for classification. But they all have different disadvantages. First, that they have large vector size, and autoencoder comprises these vectors. That's why we can increase performance and reaction time. I will not go deeply to these differences, but some important points that in unsupervised learning in autoencoder we use reconstruction instead of prediction, like in different methods, and autoencoder incidents are not labeled, so we don't need to label them. In our solution, the novelty of our solution is that we use autoencoder neural network together with blockchain, and that enables incident classification and management of threat reports. It should work in real time and could automatically organize our data and improve access to information. Also, resulting information is automatically propagated to all nodes because it's a property of a blockchain. So we don't care about this. Also, we don't care about security of transaction because it's already encrypted in blockchain. And all changes are robust and traceable, so we can have provision here. And main advantage that we reduce manual work. Neural network, autoencoder neural network is not really a black box because people think there is no transparency in neural networks. It's partly correct, but here we know which features we use to create our vectors. And that's why, having found similar incidents, automatically we can compare we know which features were used to compare, and then we can extract knowledge what is exactly happens with the neural network. We apply selection of most frequently used words, also additional dictionaries for exclusion words, inclusion words, and significant words that are important for organization. Each organization also should define their thresholds to differentiate between different threat levels. That is important for further analysis. This method should save storage space because we use compressed values for correlation, and we don't save that on blockchain. We just share them, share resources, and we automatically remove irrelevant or outdated resources. When we execute our smart contracts, they store the state on a blockchain and automatically update it. And we can synchronize data on blockchain on different nodes using peer-to-peer or proof-of-work consensus mechanisms. Here is an overview about the system. We have a user. He provides incident report from one of the critical infrastructure nodes. Then we correlate, search for similar incidents automatically before we train, of course, our autoencoder. And then we go to our smart contracts. We have here on this picture. It's acquisition, use, archival, and disposal. So incident comes first to acquisition smart contract, and after calculation of priority, using different metrics like important terms or how many original terms and so on, we can estimate priority of this incident, store the state to the blockchain in block 1. Then we proceed with use of this incident and calculate from our security policy risk points. We have different definitions for high, middle, and low security, low threat. And additionally, we apply weights because some metrics can be with more weight and some with less weight. And then using previously defined thresholds, we calculate threat level. And calculating threat level, we have our definitions, what to do with this incident. How long should we store, and so on. It is the next smart contracts archival. Also, we store status on blockchain. And at the end, they will be disposed. Here is a brief description of workflow for blockchain for incident calculation. I will go to this picture. It's better to describe. We just read incident, then we convert using backup words to a vector, then we normalize this vector counting words. We normalize to binary values, and applying deep autoencoder, we produce our threat level calculation, and then analyze it, and we can query blockchain for different state information like provision and so on. I have not so much time more. We have evaluation with almost 6,000 incident reports from open source for different topics. And here you see it's a training model of our neural network. We have input layer and several hidden layers with different activation functions. And in the middle level is important, it's level 3. We have only 10 neurons. It's a very small number, which is comprised from the initial vector. In the output level, we reconstruct this information. And so after the training, we have these 10 number values to compare using, for instance, cousin similarity. And here is a sample that we found similar incidents, how many important terms were detected, from which source, how long does it take, which blockchain ID, because we ask blockchain by blockchain ID for the incident, and calculated threat level. And we are able to visualize our information. For instance, here for 3 years of this open source incident reports, we can see different parameters and activity for different types of sources. So it's easier for analysts to understand what was happened. And here is our accuracy estimation. We're applying relative operating characteristic space plot. This red line divides the space on the good results and bad results. The better results we have, the higher on the left side we are. So perfect classification point is on the left up corner. And we see that our our results are somewhere in the near. And in the table below, you see different statistics for these different feeds, and which threats were high, middle, or low. So I have presented our system to facilitate cyber incident analysis management and classification. And we employed neural networks and blockchain for this goal. And for further research, we plan to refine our neural network model, improve smart contracts and accuracy metrics. Also, we worked without real blockchain network. We would like to check in real circumstances, because there will be delay, possibly. It will be slower. And we are also happy to have feedback from cybersecurity community.
Thank you, Roman.
Thanks.
Steve Noel from Myra.
All right, thank you very much. Let's get her loaded up. All right, so when you're trying to get a handle on a situation, to be aware of what's going on, to understand, drill down what the situation is, your operators need to rely on what I'll argue is a deep knowledge base of sort of interrelated information about what's going on in the environment. And it's kind of a problem of, having your cake and eating it too, because you need access to a lot of information that's interrelated, but it's easy to become overwhelmed with the complexity of all that information. And so what I'm going to be talking about is an approach that allows you to absorb and encode all of that dense, highly semantically rich information, and then still provide a query-driven analysis and visualization to answer specific analytic situational awareness questions. So if you'll refer to the bottom of the stack, I'm sort of this general notion that stuff that's going on in the network infrastructure is what leads to a particular security posture that you're at. And so when we started this kind of work in, say, 2001, basically, we were mapping from that lowest layer, from the network infrastructure, in terms of segmentation, firewall rules, vulnerabilities, mapping that to, if you say, an attack graph, some sort of a graph of potential attacks, multi-step through a network. And so in doing that, some of the first work that was done was using model checkers that turned out to not scale. Another idea is to try to encode that stuff in a relational database. Again, it's the wrong kind of data model for graph problems. So, we ended up doing, a lot of custom coding to solve that particular problem, because it's not just a generic nodes and edges are all equal. It's important to capture that there's nodes of different kinds and different kinds of relationships or edges in your model. And so for doing effective security analysis, you need to capture that stuff and make decisions based on that. So that meant writing custom code to handle all that stuff. But then the bottleneck becomes the effort that it takes to develop that custom code. So fast forward about 2014, we started this new direction. In the meantime, the world had invented graph databases, and so we started looking at how to leverage a graph database to be able to solve these kinds of problems. And so in particular, the most graph databases have something called a property graph model, where you have nodes, edges, and generic properties for nodes and for each node and each edge. And so then you have a SQL for graphs if you will, a graph query pattern matching language, which I'll explain more about. But the point is that the research premise was that you could leverage that architecture to solve these kinds of security problems, which I'll go through some examples of that. And so, and sort of in a nutshell, we're ingesting data from lots of different sources from up and down the stack, network infrastructure, security posture, I've mentioned already, cyber threats, for example, potential threats like the MITRE attack framework is one example, or actual detections, say from an intrusion detection system. And then finally, mapping how elements in the real world, if you will, the organizational and particularly like tactical military missions, how elements of a mission depend on stuff in cyberspace. So now you can do the kinds of analytics that I'm going to be drilling down into. So let's just say, glossing over the details, you've done what I just described. And so an analyst is now presented. So there's this kind of trade-off because on one hand, we have the flexibility of being able to build a rich kind of model that captures lots of stuff across lots of layers of this kind of a cyber attack defense stack. On the other hand, to be able to do query-driven analytics, the operator needs to be able to have a pretty good understanding of the data model so that they can query appropriately. So we address that problem by what I'm showing here is in the user interface, it actually introspects into a populated database, extracts a kind of data model. So in this case, the circles represent one or more nodes. These are like node types. And the diamonds are edge types. So this is showing that how certain nodes of certain types are related to nodes of other types through relationships of a certain type. So it's kind of an ontology, if you will. And so the operator actually interacts with this graphical depiction of the data model, which then formulates queries, which once the operator's formulated a query, executes it against the graph database knowledge base, and gets a panel that shows the result of that particular query result. And so I'm going to actually be going through examples of particular queries and the resulting matches, which are the graph visualizations that you see in the main panel there. You can also do sort of drill down to see all the properties for selected nodes and edges, or if you want to play through in time, it's got like a video kind of widget that you can play forward and backwards through time. Also some sort of aggregation by clustering nodes on the graph. So there's those kind of post-query analytics that are also part of this is a web application, so in this case, this is the browser. So one very common meta pattern I've said a lot, but it's also, I'm going to back up and say that we have applied this in a number of different operational environments, number of different data sets, and the original premise was that we didn't want to lock ourselves into one kind of problem domain, if you will. So as one example, we originally were focusing on IP networks to populate and the models and do all the queries. But more recently, and we've heard this theme earlier, is this fusion of needing to understand the situation not only in cyberspace, but within the overall context of, say, radios, electromagnetic spectrum, and EW attacks. So with this sort of generic framework allows us to fuse not only IP-based networks and situational understanding of attacks and defenses, but also, say, for example, electronic warfare. But a common kind of pattern for doing these kind of queries is to, so what it's doing is it's constraining how, if you traverse through a graph and you specify, say, some constraints for how to start the traversal, some constraints for what you do as you traverse each step, and then constrain how you stop in your traversal. That's kind of a very common pattern that we use. So, for example, if you look at certain things that are risky, say outside communications with a country of concern, or intrusion detection alerts, things that have happened that you're concerned about, then, for example, the middle of the traversal is typically sort of layers of the stack that you want to sort of concentrate on. Finally, ending constraints are typically things you want to protect. So, in a nutshell, something went boom over here, you want to trace through and see the impact on something that you're trying to protect. So, this is a toy example to illustrate some of those, and I'm going to actually use this particular graph, and we're going to run some queries and then see how those answer certain analytic use cases. And so in the real world, you would have this, hairball swarm of stuff if you were to look at the entire sort of graph of stuff that you've ingested about your environment. In this case, we are ingesting net flow from routers, which gives you the sort of pattern of how IP to IP things are communicating. Intrusion alerts, say from HBSS, which is typically deployed at the US Army, and vulnerability reports, say Nessus. So this graph depicts a mixture of all those things that have been ingested, put into the graph database, and then we're going to execute queries against that. So one sort of generic query is to say, all right, I want to, I don't know how many hops I should be looking for, but let me start at, let's say there's some alerts, and I'm going to start at the source IP for any alert, and then march through, traverse the graph, such that I land on what I'm calling a mission or mission function node. In this case, this is the mission function sort of generically represents, there's different dimensions of what you might consider mission criticality. For example, you'd have the C2 systems. Those could be supported by different IP addresses, and so there would be a node for a given, say a fire control system. Another kind of mission function would be the roles and units within a command structure, say the org chart, the command hierarchy. You could tie stuff in cyberspace to how your organization depends on those elements. So in this case, you see that you're saying from some alert, show me all the mission functions that are impacted. So in this case, we've got a set of 4 mission functions that are impacted. So let's say you want to tighten that up a little bit, and you do a little more investigation and determine that you're still going to end on a mission function. But in this case, some of the alerts, HBSS classifies alerts as being some are more severe. There's actually a field that says compromise, which saying that if it's a true positive, that apparently that machine's been compromised. So in this case, the destination IP of the alert is the red triangle. And so you're seeing that there's some alerts. In this case, there's a sort of a chain of 2 alerts that have indicated or alerted as being compromised, which then lead into this, we're calling it key terrain, which are just IP addresses that support these mission functions. So in this case, you're sort of tightening it and saying, okay, I only have time to look at the most important thing, which is, looks like I've got some compromised systems. Show me within a close number of hops the mission functions that are compromised. Another use case might be sort of relaxing in a certain way your query constraints. So in this case, we've got the .undirected by default, and this is actually a domain-specific query language that we developed, which then goes to a middle-tier service, which then gets automatically translated to the native graph database query language. Say, for example, Neo4j has a Cypher query language. There's other query languages as well that and many different kinds of graph databases. So this, anyway, the point is that in this case, we're saying, okay, we're still starting at stuff that's been compromised. Let's actually just look at key terrain, because there's different ways of defining key terrain. Maybe they don't support a current mission, for example. So this does show some additional alerts that are of concern, but not currently, let's say, mission critical. Another use case, and you probably should put this at the very beginning, is to say, how could we have prevented this stuff in the first place? Or in other words, this query says, for a particular mission function, which is function 4, show me through any number of hops all of the machines that are known to be vulnerable that support that, any particular, well, I'm sorry, function 4. So again, that's another use case. Finally, here's a use case where if you're trying to get some sort of a map of, let's say, normal behavior, and you just want to understand how your key terrain nodes are communicating with one another and how mission functions depend on those, there's a query for that. And again, in terms of a domain-specific language that expresses that. So I think I'm going to yield at this point.
Yeah, thank you.
Thank you.
And Leo Motus is our third speaker.
Thank you. I'd like to talk about the project that we are going to launch, or have been working on it for 3 years already, but officially we launch pretty soon. And that's building a system of comprehensive situation awareness for a country. As you can see, okay, so it's not too intelligent. So that's a typical stovepipe architecture, which is each chimney denotes one institution, a ministry or other bureaucratic establishment or an industrial enterprise. They are all sort of autonomous, semi-autonomous. They hate to distribute their inner information to their neighbors, typically. So therefore, the system applies two alternative methodologies for situation awareness. One is shared situation awareness, the other one is distributed situation awareness. And we also try to include social networks and minor social networks in a countryside in the ideal case. So just to give you a picture of what we mean by, or what's the scope of the covered system, we have, we have ministries, different ministries. We have subsidies or subordinated to the ministries. This is the Ministry of Defense, of course. This is Estonian Defense Forces. That's the Ministry of Interior. That's the Rescue Board, Police and Border Guard, etc. And you can go into more details. you can have more ministries. The most important part, actually, critical to life is the critical infrastructure enterprises, which are privately owned or business enterprises and are very difficult to control. But they are depending physically from each other. So that is a specific object. And on the left side of the slide are the users. Not only users, they provide also information, but basically they make decisions based on the information collected from the system. So it's nice. It's an existing system, but in order to grasp or understand how it functions, we need to formalize the picture somehow. And when formalizing, we found three groups of challenges. First, we need to model a system of system so that we reasonably mitigate the complexity. And we couldn't do that with one model or two models. We have a whole suite of models, of interconnected models. Second point is that most of the information that is being collected or is shared between the consumers is subordinated to temporal and spatial constraints, and the computing results often depend on the history of computation. So it's not like in a decent computer that whenever you initiate an algorithm with certain initial data, you get always the same result. That's not the case when the computer is connected to the real world. And of course, we need to consider that networks are disruptive and bandwidth is never sufficient. Plus, the third one is that situation awareness system attracts cyber attackers and other malign persons because it's a ready-made, pre-processed information pot. The trick is that we strive to collect the information. Sorry, I'm not very good with piano playing. The information collected through those semi-formal models and all this data and spatial dependent information can be used also for detecting cyber attacks, because we have in different applications modeled or used this sort of model for detecting emergent behavior. And cyber attack to a situation awareness system could be considered as a sort of emergent behavior. So the sooner you detect that there has been or is emergent behavior, the sooner you can make a decision what to do. It may be good for you, it may be very bad for you. So that's the trick. Just for information, it's an example of models that we have. We have meta models for describing global architecture. For actual work and simulation, we have agent-oriented models. We have specific models for checking data integrity and consistency, and also detecting emergent behavior. And we are very much interested, and we have some work done in building models for describing and analyzing interdependence of critical infrastructure enterprises. The rescue board is annually, actually every day, doing something with that sort of interdependence. And of course, cybersecurity has its own models, and we also need to consider the interests of stakeholders, different stakeholders. Naturally, we can manage with higher level stakeholders only, but for serious, comprehensive situation awareness, we need to know who and how is forming the information inside large enterprises, large bureaucratic institutions. Just a fragment of a meta-model type, and we eventually reach to the level of process. Each meta-model may have different processes, and each process needs to be analyzed separately with more detailed model. So in this case, I just show you what we do with data of the process, of those processes. We try to demonstrate the consistency and integrity of data, and that the data collected and processed satisfies temporal and spatial constraints, which is not a trivial work. And to do it seriously, we need to move from the conventional world of Turing computations to the non-classical computational models, which is illustrated here. I won't discuss it. So anyway, cybersecurity and processes, we can find or detect two types of attacks. One is attack on the critical infrastructure enterprises, which occasionally could include the attack to the databases in ministries or somewhere else. And we also could attack situational awareness system in the order of modifying data or modifying decisions or just creating fake news. And they are both essential problems, and unless we have the persistent online presence of cyber defense, we cannot actually apply or use situation awareness system. Well, we can, but the results could be disastrous. Just to illustrate a little bit more, the attackers are here, of course, and they can attack one of the critical infrastructure enterprises, which will stop working or will reduce the efficiency, and that will further influence some other critical infrastructure enterprise. So it's attack propagation In many cases, it's sufficient if you attack only one, and the attack will propagate to the other infrastructure enterprises. So we have to take care of kinetic attacks, cyber EW, and cyber attacks, conventional cyber attacks, and that makes the task slightly more sophisticated than in everyday business life. So we have something like that. The lesson that we have deduced from this survey is that we need to build into the system, into the situation awareness system, which could be just a typical information processing system, or the presence of the cyber defense. And I think that is all I wanted to say you.
Oh, great.
Unless you have
You have
questions.
50 seconds less.
I still have 52 seconds, which I present to our chairman.
Thank you. Put my pocket. Thank you, Leo. So, ladies and gentlemen, you have a time. Ask questions. Yes, please.
My question is for Dr. Noel. Your system, I understood your toy example, but what I'm interested in is if you have like a really complex network that's changing all the time, how do you manage, like how much human in the loop do you need to be able to manage all the mission requirements if they change, the functional dependencies? It seems like that would be very difficult.
Yeah, so you've touched on several things. I think maybe I counted 4, and I hope I hit each one of them. So the toy example, I had already expected that question. And so unfortunately, I couldn't show the real operational data that, for example, we've done for an enterprise network with large volumes of traffic. But I've also mentioned that we've applied it for tactical networks with their own kinds of traffic. So it is, in terms of scalability and in terms of that sort of extracting nuggets of critical information out of the very large, complex web, it is very effective at that. And part of that is that the user is able to fine-tune the query to basically more tightly constrained queries, and that will tend to make a smaller subset of the graph match. And so it's a way to tune, basically focus your attention on critical clusters. So that's one aspect, is just at large scale how effective it is, and that has proven in practice to be, because that was one of the important research questions we were going after. So yes, on that one. You mentioned time evolution, and I had also mentioned about having this ability to play like a video, like to go march forward and backward through time. So that's one way of the user gaining an understanding of the sequencing of events through time. We actually usually have this at the end of a pipeline that has something like, say, Splunk or Elasticsearch, or if you're familiar with the DISA, has something called BDP, Big Data Platform. So we've integrated with, those are 3 examples of, I don't want to call it back end, but sort of earlier in the processing pipeline to manage the dynamic ingestion. Basically gives you a way to rapidly ingest in a scalable distributed system, and then have this kind of a data lake that we can then pull into a graph database. Now, we haven't yet, there is actually what we've propose for next year's work is to, so what I just described is dynamic to coming into the data lake, but then we're doing like periodic batch pulls from the data lake, populating a graph database, let's say 24 hours worth, and then the user doing the interactive queries from that. What we're proposing for next year is to have an end-to-end sort of, because it's really about sort of continuous monitoring, so it becomes a different kind of system. What we've built so far is just an analytic sort of post-mortem kind of use cases. Hopefully I hit.
I just can add that if you have IP addressable network, so any changes to the node or links, there are programs of topology auto-generation, which help you to recover the network, of course, but it's not affecting the virtual layer or the content level or service layer. But on the physical layer, you can auto-generate.
Yeah. Another area that we're proposing for next year is to use machine learning to, so a critical part of this process is how you formulate the queries. And we're proposing that you should have this sort of adaptive process where the system is always monitoring the decisions that the human user makes. So we're trying to make it a human on the loop instead of human in the loop. So yeah, it's an evolving process in terms of capability, level of capability. But
great, right? Your question?
Yeah, I have actually two questions. Roman, why exactly did you go for smart contracts and blockchain in your solution? And the second one would be to Noel. Have you ever tested SciGraph in like any cybersecurity exercise? How did it turn out? Like, did you have good examples? Were the users overwhelmed with all the results? Like, because we saw a lot of, like, the system was like showing us a lot of details. But like, would the user be just like flooded with information, or does it actually scale down if I query it correctly? So that are my two questions.
So was that for Leo first?
Yeah. Why the blockchain?
We selected blockchain with smart cons because it enables automated or semi-automated lifecycle management for incident reports, and it reduces human involvement in this simple task. Each organization can just predefine settings and then automate some functions.
So yes, regarding exercises, we have. SciGraph has been applied in one military exercise, and that was successful in terms of being able to manage the complexity. In other words, to be able to craft some query, and it actually was what I described was patterned after that, the blending of HBSS alerts, NetFlow, and vulnerability scans. Yes, on being able to. Basically, you can look at local neighborhoods of things. So turned out there was really just one alert in this particular exercise, and plenty of, say, a dozen different mission command systems involved, and so there were like 2 mission command systems that were at risk because of that particular event. And one thing that we did not accomplish in that first exercise was. There was the final portion, which is mapping from the mission objectives to, or let's say organizational units to the IP space. We had to do that manually. We're actually I'm going to be going actually to an exercise next week, or preparing for one next week. And our goal there is to do more automatic ingestion of mapping IP space to military organization space.
Thanks. More questions, please? Yeah, on the back.
Hello, Joe Hatfield from the United States Naval Academy. This is for Dr. Graf. I don't know that I followed it completely, so please correct if any of this question doesn't make sense, but for effective situational awareness, any kind of in neural network would have to learn not just before it hit the situation at hand, but in real time as well. And but the model that you showed with the blockchain seems, or at least if I understood it, each smart contract would there was an iterative storage on the blockchain such that new blocks would need to be kind of iterate through the smart contract flow. So in back of my mind, I was thinking about Ethereum's problems with scaling, and I wondered if that had presented any problems for you in terms of, is their validation rate sufficient for your use today? And if your solution is adopted widely, would that present a problem unless, of course, the Ethereum core developers can implement the various techniques they've talked about, sharding and other off-chain, on-chain kind of techniques to try to increase the block validation rate. But I just wondered if that problem with Ethereum is presenting any issues for you and the implementation that you propose. Thank you.
Thank you. Currently, it's just a prototype, and the blockchain is used just to save a state on a blockchain that we just, it's just small information, and whole information is saved in data model, also in neural network model. And neural network will be constantly updated with new data. So,
just one comment, just to make here, there is two issues here. One is incident analysis and recognition, which is done by the neural network.
yeah.
And the other one is a memory organization, which is done by blockchain. So basically, they are two interconnected processes.
Yeah, classification,
but they
search.
are separate.
Yeah, they're independent.
More questions? Okay, let me entertain myself. I have a question to Leo. I know it's a hard question, but still I ask you. You mentioned point number 2, challenges, is completeness and integrity of the knowledge. And you have these pipes, and they are not talking to each other. And each pipe has its own God and its own model of truth, which might be conflicting. So how you put them together, and even more, trying to solve the inter-pipe conflict before you go to the inter-pipe integrity?
We will never try to change the behavior of each individual process. When we collect,
so you leave the pipes as they are?
Yes. We leave the pipe for the technical people who actually run the pipe. When we collect information for situation awareness system, this collected information will be processed, fused, and merged, and whatever processes are being done for more comfortable handling for the decision makers. And this fusion process is very sensitive to the temporal and spatial constraints of different processes, because we hate the idea of getting involved with semi-autonomous processes. Every industrialist knows what to do, how to run its own enterprise. The problem for the situation awareness system is that you have to coordinate different enterprises so that it's useful for the country as a whole, or somebody in the country.
Yeah. Great. Okay, please, questions? Let me make some comment. Meanwhile, you can think about that. We are trying to introduce AI, which really means, without going too much into depth, the first question is, if you say something, if you store something, some node or link, or you want to do something, you have some intentions, some goals, my first question is, why the heck you mean about that? What do you really mean? So all the models, what we're using here, are not so much analytical, but they are symbolic. So we try to model because we humans, we don't think about, Markov chains or how to compute the threshold functions for the neural network. We simply think about. So it doesn't mean that traditional analytical methods are invalid. It means that two aspects of intelligence, cognitive and computational aspects, should work together. So the talk that Roman presented was actually in the border of that. He had this neural network computational side, but he had also the dependencies between the records in the blockchain. And nobody knows yet how to build flexible blockchains. They are great because they are secure. But are they enough flexible, like our human brain is flexible when we store and restore, and we remember and we recover, and we make inductive reasoning? Are they good enough? They are excellent for securing information because they were made for the, for these financial transactions. But this is an area of great future research, how to make blockchains flexible so that they, in some sense, of mimic flexibility of human body. The work that Leo was reporting is probably one of the first efforts, except few countries, who are trying to do comprehensive statewide information or situation awareness system, because you really can't imagine how conservative are people, how conservative are institutions and agencies protecting their own turf. They follow the idea, if this is working, I don't want to change it, even if my neighbor does the same thing and does the same thing better. I don't want to change. So what he has, or his team has to build, is so-called very flexible ontologies, the conceptual, metaphysical classification of all the things, all the entities and relations and intentions and beliefs and actions and events and behaviors, and so that all this is orchestrated in a fashion which is flexible. So otherwise, we cannot do AI, we cannot do inductive reasoning if we don't have solid formal models about that. And the talk that Stephen was talking is, currently our cybersecurity is, what is the most important thing in cybersecurity now? At my low level, infrastructure is safe. Okay, the network is safe. The servers are safe. The services which use data from the databases are safe. And if this is everything is safe, I can recognize my cyber attack. I can mitigate my cyber attacks. I can know my vulnerabilities. I order new patches. And if this works, I have done great work. But if nobody uses this, and this is a change now, the quality of IT security is measured not anymore about the quality criteria defined inside the IT world. It is measured how well this IT structure is serving the missions. So the idea is how to build safe missions which ultimately meet their goals, even if my underlying IT structure is maybe compromised. So like some famous US mathematician said, how I can do reliable computations if my elements are unreliable. So, and this is exactly the emerging behavior. So this is emerging behavior of the network, which gives a new quality, which cannot be a sum of mechanical qualities of each node. Do you have more questions? We have 3 minutes, 47 seconds. If not,
well, I think we can go early into the break, otherwise.
Exactly, we do that.
If you guys don't mind. Thank you to all of you. It was a very interesting panel, even though it was quite theoretical, I have to say. But for all of you who are interested in the papers, like we do have 2 papers in this panel, and please do not hesitate to take a look at the proceedings book, where they are more explained in depth. Where you can actually read through it and like go over it all again, because like those graphs are like kind of shocking if you see them again, I have to say. Well, thank you all of you, and enjoy the break, and we will see you back for the next breakout session. Thank you.